Let's take a look at a source-free RC circuit. That's the dual or the analog of a source-free RL circuit. So RC, resistor capacitor circuit, RL, resistor inductor circuit. So our RC circuit will just have a resistor and a capacitor. So if we draw our resistor and our capacitor, or our resistor and an inductor, right? So there's RL and there's RC. We talked about a series RL circuit, that's our L, where we tried to find the current through the inductor IL based on some initial current, because it's the initial current, omega L, is equal to 1/2 L I squared, that stores the energy in the inductor. So we talked about this as being in series. The dual of series is parallel. So we have a parallel RC circuit where what we're trying to find in the RC circuit is the voltage across the capacitor. You know, the voltage, there'll be some initial voltage across the capacitor, VO, VC of 0, because the energy stored in the capacitor, that's 1/2 CV squared. Right, so here we have our IL of 0 is our I naught. So we'll look at it in terms using our duality. Series is the dual of parallel, and inductor is the dual of a capacitor. Now the dual of a resistor is a conductance, but it's still a resistance. So the source-free RC circuit is actually much more common resistor capacitor than an RL resistor inductor circuit. It also models our ideal model of a capacitor more accurately models the physical device. We would model the losses in a capacitor as a resistor in parallel with it. We would model the losses in an inductor as a resistor in series with it. So if we go back, we'd still end up with similar models if there was just the two of them, because they're both in parallel and series when there's only two elements. So this RC circuit's better agreement in that respect. There's smaller losses in a physical capacitor. Capacitors are smaller, lighter weight, and actually they're more applicable to integrated circuit applications. Integrated circuits, we have to consider the capacitive effects and the RC effects there. So here's our model for our circuit diagram for an RC circuit, just a capacitor and a resistor, knowing that in order for there to be any current flowing, there must be some energy stored in this capacitor, and it's stored based on the initial condition of the voltage, or V at time 0. If we're looking at our initial time as 0, we typically do, that's some V naught. So if we did our KCL equation at this top node here, the current through the capacitor, right? That's that IC, that's our CdV dt, and our IR, up at the bottom, that's our V over R, that's our IR. So that's got to be equal to 0. So if we organize our differential equation so that our dV dt doesn't have has a coefficient of 1, then we get dV dt plus 1 over RC times V is equal to 0. So that's our source-free RC differential equation, or DIPEQ. Using the concepts of duality here, we can compare it to what we came up with for our RL differential equation for just an RL circuit. If we let our voltage go to current, and we let our 1 over R go to R, and we let our L, or I guess in this case C, go to L, we end up with, we can see that these are the dual of each other. So now we'll be able to analyze, since the differential equations are the dual of each other, we can use our solution to the RL circuit, where our current through the inductor was our initial current, I naught, e to the negative R over L times T. That dual solution is the voltage of the capacitor is the initial voltage V naught times e to the negative T over RC, which is our V naught e to the negative T over tau. Whereas this is our tau C, where for a capacitor, tau C is equal to RC. We could also say this is I naught e to the negative t over tau L, where our tau L is equal to L over R. So the time constants are also the dual of each other. If we think of it in terms of the time constant, there's an RC. We could also look at this circuit instead of taking the KVL equation, we could, KCL equation, we could do a KVL around the loop. So if we go a KVL around this loop in the direction of the current, we get the voltage across the capacitor, 1 over the capacitance, integrating from our initial time to time t of the current, dt over time dt. Then we got to add back in that initial voltage. And then as we go through the resistor, we get our plus IR, that's equal to 0. So there's our KVL equation. We could take the derivative of both sides of this equation. Well, dv dt of 0 is just 0. We take the derivative of, with respect to time, of the integral of the current with respect to time, we just get the current I. So we get I over C, and then of course the derivative, this is a constant, this voltage at time t is equal to 0 is a constant, so the derivative of that is 0, and then we just get R times di dt. So if we apply that here, that our I must be equal to this V over R using Ohm's law, then we get, substituting for I, V over R, so we end up with V over RC plus our dV dt here, since we get a whatever dV dt over R times R, the R's will cancel. So we can then analyze this differential equation, dV dt plus 1 over RCV. We can assume a solution. If we assume a solution instead of just using the concept of duality, we'll assume that it's also an exponentially damped function with some initial coefficient sitting in front of our exponential e to the st, where s has some frequency. Then we can substitute that in to our original differential equation. When we take the derivative, we get SA e to the st. When we just plug in V, we just get 1 over RC A e to the st. Pulling out A e to the st, we get that this term here is our characteristic equation that we must set equal to 0. So that characteristic equation, we get the frequency, S is equal to 1 over RC, and the time constant tau is equal to RC. So we end up with a similar type graph. Instead of current versus time, now we're looking at voltage versus time, where our voltage in this parallel RC circuit, which is the voltage across the capacitor, V naught e to the negative t over RC, or V naught e to the negative t over tau. It still has that form of e to the negative t over tau, so we can talk about the time constants of a circuit. So we see in this circuit, if we increase the resistance, we increase the time constant. So the time constant moves further to the right, and our energy hangs around for longer. Whereas in our RL circuit, when we increase the resistance, we decreased the time constant, because it was the current that was storing the energy through the current. So now we're storing the energy through this voltage, so we limit the current if we increase that initial voltage. Okay, so that's it for this video. We'll do examples of RC circuits in other videos.